lecture. Okay. So we will finish this chapter and then hopefully talk a little bit about the representation learning. Okay. Next lecture we are going to talk about the autoencoder. Okay. That's about it for this semester. Okay. So the week after next is going to be the final exam. Okay. And one thing to tell you guys is that, okay, the department actually has an announcement to make. Okay. Because they want to reach as many vocational students as possible, and it took. This is not for you guys. Okay, it's for night class. Okay, for night session. So never mind. Okay, but okay. So the week after next is going to be the final exam, and then the third lecture. Okay, from today is going to be the project presentation. Okay, for the final term project, and for that day. Okay. The TA is going to, randomly decide an order, okay, for your presentation, okay. So the TA will announce the order a week, at least a week prior to that day, okay. And each presentation is going to take maybe, because in the afternoon session, it's going to be quite a few groups. So we will see each presentation. I mean, it's going to be maybe between 10 to 15 minutes, depending on how much. I mean, we will decide about the length of the presentation. Okay, and announce that maybe. Through the class, and during that day, okay, we will provide a pizza, okay, for you guys, okay, as usual, okay. So you guys are more than welcome to come a little bit early, like around 12:30, okay, to enjoy the pizza. Okay, before your presentation, okay? And some students asked me about the final exam. I mean, is it okay to bring the one-page cheat sheet? Okay. Yes. Okay. You guys are allowed to bring one-page A4. Okay, cheat sheet. Okay. Whatever you wrote on that page. Okay, I don't care. Okay. But it's not going to be a whole book, okay? Just one page, okay? And I think everything remains remains the same, just what we, how I told this class last time, okay? So hopefully, you guys have a better understanding. And already, by the way, I already have the sample final uploaded to the EE class. Okay, so just in case if you don't know the format of the final exam, please go check it out. Okay, we normally provide a little bit more questions than required. Okay, so that you can have a little bit of wiggling room. Okay. You can drop one or two questions, in your final exam. Okay, hopefully, this is going to help you to get a better grade. Okay. So, okay, so back to our lecture, okay. So last time we talked about the RNN, right? And we actually create a model that is used to predict like the time series data, okay. Originally, we want to create, we want to predict like just one time step, okay. But later on, we say, okay, now we want to predict like 10 time steps, okay. Then, okay, we found that if you apply like the model that predict like the next time step 10 times for those 10, additional time steps, it's going to, the performance is going to be very poor because like the error actually gets accumulated. So what we can do is that we can convert, we change the model so that it predict like the next 10 time step like together, okay, just in one prediction. This way you avoid like the issue of like error accumulation, okay. So yes, so the performance, okay, if you use that this model, yes, it's going to perform much better than using like the original model to do like a prediction 10 times. Okay, but actually, okay, you can even you can actually like convert, because the previous models that we talked about, okay, they are all like sequence to vector models. Okay, so we can actually convert this sequence, our sequence to vector model into sequence to sequence model. So what is the difference? Okay, in the sequence to sequence model, it's something like this. Okay, yeah. Instead of training the model to forecast the next 10 values only at the very last time step, okay, we actually, in the sequence to sequence, we train it to forecast the next 10 values at each and every time step. So it's going to be something like that. Okay, you get the first 10 steps, first 10 values, and use that to predict the next 10 values. And then, okay, you move one step ahead. Okay, so say like, okay, say this is like, okay, so this is the first 10. So you are going to, your model is going to use this first 10 values to predict the next 10 values. Okay? And then, okay, your model is going to move one step. Okay? So the next is going to be something like this. From the second element to the 11th. Okay, so this is going to be the next sequence. Okay, the second next 10 element, and you use that to predict like from here to one more element. Okay, something like that. Okay, so you predict this. You use this to predict this one, and then you move one step and you predict next 10, and so on. Okay, so that's the idea. Okay, so basically, okay, the advantage of this technique, okay, the loss will contain a term for the output of the ion at each and every time step, because now, okay, originally you use the whole sequence, and then you only account for the last output, the loss, okay, only accounts for the last output, okay? But no, because, okay, for every, like, for example, from here, you predict the next time step, and you can use this to compare with the ground truth, well, for the loss, and you can use that, I mean, to fix, to get the gradient to fix your model, okay, to improve your model. So you get a lot of error gradient, okay, compared with the original approach, okay. So yeah, so because you get a lot of gradient, I mean, in flowing through the model, so this gradient will both stabilize and speed up training. So what do we do? Okay, the first thing we need to do, obviously, is to prepare our data so that, like, we take the first 10 and then predict the next 10 and so on. Okay, but actually, what we do is, you know, not exactly like this. We are going to create what we call a causal model. Okay, so it's not like you use first 10 to predict the next 10. We are going to use the first 10 to predict. To predict like this from first 10. This is the first 10. Okay, and then we want to predict here, from here to from the second element to the 11th. So there's we only predict like one additional element in this round. Okay, and then we move up from the second element to the 11th. We predict like the third one to the third one to the 12th element. So every round we only predict one more. Okay, and the reason this is called the causal model is because like you can see, in this case, okay, because you use the first 10 elements, and you predict like from the second element to the last one plus a new element. So some part of the input somehow overlap with the output, right? So that is why this is called the causal model. There's overlap between your X train and Y train. X train is your input. Y train is your ground truth. Okay. So what you need to do is here. Okay. You need to prepare your data accordingly. Okay. You have your X train ready and you have your Y train ready. Okay. And then after that, okay, you also need to change the model. Okay. Remember, now it's a sequence to sequence, right? So your input obviously is still, it's a set. It's just a sequence. Okay. But the output is going to be a sequence. So remember, like originally, okay, these two lines remains the same. Okay, we have like a simple argument. Okay, return sequence equal to true. Okay, and this part is the same. However, here, okay, originally we used like just the dense layer with 10 elements, right? With 10 neurons. But now, okay, because we want to convert it into the sequence, so we can wrap this layer by the time distributed, okay, so that we make the last make the output a sequence as well, okay. So this time distributed is going to convert the output into the shape of the sequence, okay. So supposedly if you use the dense layer and and train it using like the sequence to sequence, it's supposed to work as well, okay. But the reason to add the time distributed dense, okay, to wrap this dense layer with the time distributed is to make it more verbose that you want this output to be sequenced, which is normally a better practice because because dense can be used for either the vector output or sequence output. But if you don't wrap it with the time distributed, we don't know what type of model we are doing here. So it is a better idea to make it more verbose. Okay, make it obvious. Okay, here we are dealing with a sequence-to-sequence model. Okay, and then there's one small tiny detail that we do need to be careful. Okay, we train it everything looks just right, but there's one thing. Okay, because now remember, every time we use this 10, the first 10, and we predict the next. Well, the window that should one element, we predict that, and then and so on. So, but yes, this is going to be used for training, but for evaluation, when it comes to evaluating the model, the only thing that matters is because eventually, say we have the first 50 element. Obviously, with this shifting, you are able to do this many times. But the thing that really matters is this next 10 values. This next 10 values. We want to see the error, how much error this last 10, the future 10, or I should say the 51st to the 60th element. That you predicted, how far away they are from the ground truth. This is what we really care, right? The previous, value, we will use that for training, but we are not going to use that for evaluation. But during evaluation, what matters is the accuracy of the 51st to 60th. Okay, element. So you should define a separate MSE that care only for the last time step. Okay. So we define this. Okay, this return Keras matrix, mean square error. Okay, the last one. Okay, and then once you define this last time step MSE, you can have your optimizer. Okay, we use added here, and then we compile our model, which use the loss function MSE optimizer. Okay, matrix optimizer is the added. Okay, the matrix is last time step MSE. Okay, so these two are different. This one is to measure the performance of the model. This one is used during training. Okay? You need to be very careful to understand the difference between these two. Okay? So if you use this and train this model, the MSE you get is about 0.006. Okay? The previous one gives you the MSE of 0.008. So this one is 25% better than the previous model. The previous model is the sequence to vector. This one, sequence to sequence, give you even lower MSE. So this is a better approach. Okay, 25% improvement is not is significant. Okay, so obviously you can combine this approach with the first one. What do I mean? Okay, for example, say you want to predict like the long-term time series. Say like okay, use the first 50 time steps to predict next 50 time steps. Then what you do is that okay, you use this one to predict the next 10 value, and then use this sequence to predict the next 10 time value and so on. So you can apply this thing 5 times to predict like the next 50 values. So sort of like combining the first approach and the second approach. So obviously, I mean, when you do that too much, okay, you still get like error accumulation, right? So you know, when you should weigh weighing how many additional sequence you want to predict. I mean, each time. Okay. So for example, okay, if you use like the first 50 to predict the next 10, okay, that's reasonable, right? That's reasonable, okay, because you should have enough information to predict the next 10. But let me use a very, extreme example. Okay, say you have the first 50 value, and you want to predict like the sequence of the next 100 sequence. Then, okay, you can use the first 50 to predict next 10, and do it 10 times, right? Okay, so that's what we meant by combining these two approaches. Okay, then I mean, because each time you get the 10 additional value, and then you do it 10 times, you get the next 100 values. Okay, but if you say, oh, I don't like error accumulation, let's do it in one prediction. So you use the first 50 to predict next 100 in one try. Probably that's not going to perform very well. Why? Think about that. You don't have a lot of information to predict this long, right? In one prediction. Okay, so this is like a trade-off here. Okay, I mean obviously like if you have a long sequence and you predict like a shorter sequence, it will give you a much accurate prediction, and then you can tap on that more accurate model. I mean several times. Okay, to form a longer prediction. Yes, but on the other hand, okay, if you use a shorter sequence and you expect to predict like one long sequence in just using, you want to train a model to do that. That model, most likely will not perform very well. Okay, it's just because you don't have enough information. Okay, so this is like which these two approaches, yeah, they can be combined. As for like how do you combine them? That's something you can think about. Actually, for the project 3, okay, you are required to predict like the next 6 hours, PM 2.5, right? So say, if you just use the previous 3 hours to predict next 6 hours, well, most likely it's not going to perform very well. Okay, just want to give you an idea. You probably want to use a much longer sequence to do the prediction in order to make it like the next 6 hours prediction better. Okay. So also, okay, when you forecast a series, okay, it is useful to have some error estimation, okay, for your prediction, okay, like how accurate or how bad your prediction is, okay. So for this purpose, okay, the NC dropout is a good technique to apply okay, we talked about MC dropout in chapter 11, okay, 2 chapters, ago, okay, so basically you can add MC dropout layer, okay, with each memory cell, and this will help you, to estimate what we call error bar, or like the variance, okay, of your prediction. So which will you get a mean and a standard deviation, okay, which will help you to determine, okay, if your prediction is trustworthy or not, okay. This is important. For many time series forecasts. For example, like if you want to predict like the stock market trend, okay, because you are investing money on it, right? So obviously you want to make sure, okay, your prediction is accurate enough, okay, so that your money you invested is not going to be a waste, okay. So, okay, at this point, okay, we finished like a lot of discussion but as I mentioned at the beginning of this chapter, okay, there are, the island has some issues that we need to deal with, okay. Yeah. So, for example, when it comes to predicting the forecasting time series or handling other kind of sequence, RNN, is used for that purpose, but they do not perform well on long time series or sequence. Why? Okay. So first, to train on long sequence, okay, we must run it over many time steps, making the unrolled RNN through time a very deep network. Here, when we say a deep network, I'm talking about here. Okay, we need to, unroll many steps. Okay, so when I say it's going to be a deep network, I'm not talking about the depth here. I'm talking about the depth horizontally. Okay, because you are going to expand your island through many time steps. Okay, which will create some issue. Okay, because the depth is not there are two depths that we are discussing here. One of the depth is the number of layers, which is the same as like as we discussed for the other networks such as CNN or MLP. But the other depths, this unrolled through time. Okay, this is especially, the case for long sequence. Okay, and this type of thing, okay, only is this issue only happens in RNN. Okay, you don't have that in CNN, you don't have that in MLP. Okay, so I just want you to be aware. Okay, why training a long sequence? Okay, you encounter issue. We need to explain, we need to discuss, here, different. Where is it? Okay. Okay. So these are, okay, when it gets deeper, okay, even though we are talking about, the other dimension, deep other dimension, okay, yeah, the network, okay, the training of the network may suffer from unstable gradient problem, okay, so it may take forever to train, or training may be unstable, Okay, another issue, okay, when RNN processes a long sequence, it will gradually forget, what we did at an earlier sequence, okay? So the first input in the sequence, it will gradually be lost, okay? Especially during the unroll through time process. So what do we do? Okay, so, let's talk about these two problems, okay, two issues. How do we solve that? Okay, the first issue, okay, unstable gradient problem, okay. Yeah, we talk about many ways to deal with that, especially in chapter 11, okay. So, for example, like, good parameter initialization, remember the He initialization, or Glorot initialization, all those parameter initialization, or faster optimizers. We talk about Adam, we talk about Nathan, all those optimizers, or dropout. Okay, this, okay, this actually still helps. They are still useful. They are still useful. Okay. However, okay, one thing is slightly different. Non-saturating activation functions such as reloop, okay, may not help as much here. Okay. Why is that? Okay. They may actually lead the RNN to be even more unstable during training. Okay, because when you're doing gradient descent update, okay, the weights in the way that increase the output slightly at the first time step. Okay, well, here. When you're doing the gradient update, okay, keep in mind, okay, this training, okay, for one iteration, okay, this expansion, or like unroll through time, it's just one iteration, right? So this gradient flow back, okay, even though I show you, okay, they look like okay, you have this and this and this and this, they are different model, right? They looks like a different model, but they actually, all this represent the same thing, right? All this represent the same thing. So when you are calculating the gradient, yeah, you are calculating the gradient for this, but actually this and this and this, they actually share the same weight because they actually are the same thing, right? Even though we are unrolled through time, but they represent the same stuff here. So they use the same weight. All these weights are the same, and this is during one iteration. So if your activation function result in slightly larger result, then those larger result, because you are using the exactly same weight, that slightly increased result is going to be enlarged and enlarged to a point that it explodes. Okay? So because this unroll through time is special in our, as I said, this is not going to, we don't have that in CNN, we don't have that in MLP. So in the MLP, okay, when you train a layer, say, if you, of course, CNN or MLP, it's going to be like, we don't have unroll through time. So actually, when you train a layer, okay, something like this, of course, they represent different weights, right? Each layer has different weights. But now, okay, all these have the same weight. So that's the primary difference. Okay, the primary difference. So, okay, the same weights are used at every time step. Okay, So the output at the second time step may also be slightly increased, and so and the third step, and so third time step, and so on. So eventually, okay, the output until the output explodes. Okay, so because when we say non-saturated, I'm talking about. I mean, you know riddles like this, right? Right? So you, I mean, this value can go very big, right? This value can go very big. The result of the riddle activation function can be very big, right? After you apply riddle, I mean, it could be very big. But on the other hand, the saturated activation function, okay, such as hypertension, okay, the value is, the result is in between -1 to +1, right? Okay, so it is bounded, right? Yeah, we have the saturating function. The issue is like the gradient is going to be very small. Yeah, we have that issue as well, but at least like the output is not going to be, like unbounded. Okay, so the saturating function, such as like hypertension, okay, does not have that issue, does not have that risk. Okay, so that is why, okay, the hypertension in the RNN is normally used as the default, Okay, I'm not saying riddle can never be used, but I'm just saying, I mean, in RNN, riddle is not as popular as hypertension. Okay, not as popular. Of course, you can say, oh, I mean, how about gradient? Because saturation function have that vanishing gradient issue, right? But as I said, like in other, most of the issue comes. I mean, when we say in the other, the unstable gradient, I mean, what the unstable gradient in other actually normally refer to exploding gradient, because like it's somehow like I mean, especially in long sequence training, okay, either gradient or like the result function gets enlarged and enlarged, okay, eventually explode, okay, but yeah, I mean, yeah, for saturating function, I mean, if you have that vanishing gradient problem, we already know a lot of technique to fight with that. We already know a lot of techniques, okay, especially the ones that we learned from the chapter 11. I mean, they are still okay. Okay, another way, okay, yeah, the gradient, let's say, okay, explode too, okay. So if you notice that training is unstable, most of the case is because of the exploding gradient, okay. So you may want to monitor the size of the gradient, okay. And how do we monitor the size of gradient? I mean, we talk about TensorBoard, right? TensorBoard is able to allows you to monitor the gradient, like during training, okay. And if that happens, you can also use gradient clipping. We talk about gradient clipping in chapter 11, right? Okay, which help you to prevent gradient, exploding gradient as well. Okay. So, yeah, and remember, like in chapter 11, I mentioned like batch normalization is important technique, right? I mean, this is so important that in chapter 12, I mean, when we talk about CNN, I mean, you see batch normalization. I mean, always used like right after the convolutional layer, Okay. Yeah, I mean, how about in RNN? Yes, we can still use batch normalization, but you know, there's some research that you know, they found out that BN was slightly beneficial only when it was applied to the input, not to the hidden layer, hidden state. Okay, so because if you try to apply batch normalization directly, then it will apply to both the input and the hidden state, because hidden state is also considered, I mean, that's the feedback, remember? I mean, that's also considered as the input of the neuron, okay? So in other words, okay, you know, you're slightly better than nothing when applied between recurrent layers, okay? Well, but not within recurrent layer, okay? So, so basically, okay, in Keras, okay, this can be done by adding a batch normalization layer before each recurrent layer. But the issue is, yeah, I mean, the batch normalization, you cannot expect the BM help you a lot. It's not like convolutional neural network or I mean, you know, the other cases like BM help a lot. Okay, I mean, instead, if you say batch normalization doesn't help that much, what else? What other option do we have? Okay, there's a concept called layer normalization. Okay, which was proposed in a 2016 paper. Okay, this concept, I'm sorry, is similar to batch normalization, but instead of normalizing across batch dimension, it normalizes across feature dimension. Okay, so it normalizes your features. Okay, based on different features. Okay, so the advantage of this is that it can compute the required statistics on the fly at each time step. So you don't need to remember in the batch normalization. If you still remember our discussion, in chapter 11, you will know that batch normalization during training and during inference act differently. Remember? Because during training, you have the batch, right? So you get those statistics from each batch easily. But during inference, because you may not have that batch concept, right? So you actually have to, estimate those statistics, okay, from during the mini batch, from the mini batch, training, process, okay, and use that in the inference. But the layer normalization, okay, it remains the same, okay, regardless. It's you are doing training or you are doing inference. Okay, so it's a much easier, process. Okay, so normalization will learn, scale, and offset parameter for each input. Okay, directly, and in RNN it is typically used right after linear combination, and before and the hidden state, and before the activation function is applied. So, we can implement layer normalization in Keras, okay, with a simple memory cell, okay. So this is an example, okay. Class layer normalization simple RNN cell, okay. It is a subclass the layer, okay. And here, okay, these are, pretty much, very, very easy, okay? So, we don't need to change that much. The only thing we add is here. We create this layers, layer normalization. Okay, but remember, we don't specify their relationship. Like in here, we specify their relation actually in the call method. So here, okay, you can see that, okay, we first compute the output, okay, first, and then, okay, we apply the layer normalization to this output. Okay, oh, by the way, the output and new states, they are the same, because it's a simple RNN cell. We know that, right? And the output and the state are the same. So then we apply the layer normalization first before we apply the activation function. Okay? And then we just output the same thing twice. The first one is used as an output. The second one is used as the state. The state is actually a list because, in general, the RNN cell can have more than one state. Okay, so that is why it is like a list instead of just one value. Okay? So, yeah, I think I already explained what this code is. So, yeah, not much to explain here. And then you can use this LN simple RNN cell to create a model like this. Model, okay, still use sequential API. So in the layers RNN, okay, you use the LNS simple RNN cell, okay, to create like 20 this. Yeah, this is a simple RNN cell. Yeah, this is simple RNN cell, and we use that to create. To create a simple RNN cell with the layer normalization. Okay, we have 20 simple RNN cell with the layer normalization, and the other parts remains the same. Okay, we apply this LN simple RNN cell. Okay, and the other part. So up to now, okay, this is like one technique you could use, okay, to improve the training and the fight with the exploding gradient in RNN. Okay, so let's take 10 minutes break. When we come back, we will continue our discussion on the other technique that help you to train RNN.